Welcome to the discussion. Today, we're diving deep into a new architecture for large language models, the Differential Transformer, or Diff Transformer, as detailed in the archive paper 2410.05258V1. This paper claims significant improvements over traditional transformers. Let's start with the core problem the Diff Transformer aims to solve. What is the primary limitation of standard transformers that this paper addresses?
Standard transformers often suffer from overallocation of attention to irrelevant context, which the authors term attention noise. This noise can drown out crucial information, hindering performance in tasks requiring precise information retrieval or robust context understanding. The paper argues that this noise significantly impacts tasks like long context modeling and key information retrieval.
So the core idea is to reduce this attention noise. How does the diff transformer achieve this noise reduction? Can you explain the differential attention mechanism in detail?
The key innovation is the differential attention mechanism. Instead of a single softmax attention map, Diff Transformer calculates the difference between two separate softmax attention maps generated from partitioned query and key vectors. This subtraction acts as a form of noise cancellation, analogous to noise-canceling headphones. The resulting attention scores are sparser, focusing more on relevant information.
The paper mentions a learnable scalar, the differential attention equation. What's the role of this parameter and how is it learned? What is the significance of its initialization strategy?
AGA controls the weighting between the two softmax maps. It's learned during training, allowing the model to dynamically adjust the balance between the two attention maps. The paper explores different initialization strategies for AGA, finding that a layer-dependent exponential initialization generally performs well, but the model shows robustness to different initialization choices. This dynamic adjustment is crucial for effective noise cancellation.
The paper presents expensive experimental results. Let's focus on the scalability aspect. How does the diff transformer compare to the standard transformer in terms of scaling up model size and training tokens?
The scaling curves show that Diff Transformer achieves comparable language modeling performance with significantly fewer parameters and training tokens. The paper estimates that Diff Transformer requires approximately 65% of the model size or training tokens needed by a standard transformer to achieve similar results. This suggests a higher efficiency in resource utilization.
Beyond scalability, what other advantages does the diff transformer demonstrate in the experimental results? The paper highlights several downstream tasks.
The Diff Transformer shows significant improvements in several key areas. It excels in long context modeling, effectively leveraging longer sequences. It also demonstrates superior performance in key information retrieval tasks, particularly when dealing with multiple distracting pieces of information. Furthermore, it mitigates contextual hallucinations in tasks like question answering and text summarization, and reduces activation outliers, which is beneficial for model quantization.
The reduction of activation outliers is an interesting point. Can you elaborate on the implications of this for model quantization and efficiency?
Activation outliers, those significantly larger activation values, pose challenges for quantization, often requiring higher bit widths to represent them accurately. Diff Transformer's reduction of these outliers allows for lower bit quantization without significant performance degradation. This opens up opportunities for more efficient model deployment and inference.
The paper also discusses the integration of flash attention. How does this impact the efficiency of the diff transformer?
The authors demonstrate that the differential attention mechanism can be efficiently implemented using flash attention, a fast and memory-efficient attention mechanism. Their experimental results show comparable throughput between diff transformer and standard transformer implementations using flash attention, suggesting that the efficiency gains of flash attention are preserved in the diff transformer architecture.
The paper includes ablation studies. What are the key findings from these studies regarding the design choices of the diff transformer?
The ablation studies confirm the importance of the differential attention mechanism itself. Removing group normalization, for example, negatively impacts performance, highlighting its role in stabilizing training. The relatively small impact of different initialization strategies further underscores the robustness of the overall architecture.
The paper mentions in context learning. How does the diff transformer perform in this area, and what are the implications of its improved robustness to order permutation?
In many shot in context learning, diff transformer consistently outperforms the standard transformer across various data sets. More importantly, it exhibits significantly greater robustness to the order of examples in the prompt. This is a crucial advantage, as traditional transformers often show sensitivity to example order, leading to unpredictable performance variations.
Let's return to the core concept of attention noise. Can you summarize how the differential attention mechanism addresses this issue and its overall impact on the model's performance?
The differential attention mechanism effectively cancels out attention noise by subtracting two softmax attention maps. This leads to sparser attention patterns, focusing the model's attention on relevant information. This improved focus translates to better performance across various tasks, including improved scalability, long context understanding, information retrieval, hallucination mitigation, and in-context learning.
The paper concludes by suggesting future research directions. What are some of the most promising avenues for future work based on the diff transformer?
The reduced magnitude of activation outliers opens up exciting possibilities for developing efficient, low-bit attention kernels. The sparser attention patterns also suggest opportunities for compressing key value caches, further enhancing efficiency. Exploring these avenues could lead to even more efficient and powerful large language models.
This has been a very insightful discussion. The diff transformer presents a compelling alternative to standard transformers, offering significant improvements in efficiency and performance across a range of tasks. Thank you for this detailed explanation.